Hi, this is Dr. Divya Bartaria, the Head of Corporate Relations, United Group of Institutions, Prayagraj, and the Associate Professor in Chemistry, Department of Applied Sciences and Humanities, United College of Engineering and Research. I welcome you all to this second session of solid state analysis, in which we will discuss imperfections in solids. After discussing significance of imperfections, we will also emphasize upon the impact of various imperfections of crystal structure and properties. The entire study will basically focus upon point defects and its impact. So, today the agenda will be imperfections in solids, why study imperfections in solids, crystalline defects, point defects, and under point defects we will discuss vacancy defects, self-interstitial defects, Frenkel defects, Schottky defects, and finally non-stoichiometric defects. So, let us come to the first and the most important thing, that we need to understand what do we mean by imperfection in solids. So, all of us know that nothing is perfect. The crystalline structures that we have looked at all have imperfections. So, an ideal solid with all the atoms orderly arranged does not exist. So, all solids contain large number of various defects or imperfections, and that is why we are here to discuss imperfections in solids. Now, the question is, why study imperfections in solids? Why is it important to study the imperfections when we talk about the perfection everywhere? So, this must be clearly understood by all of us, that the properties of the materials, be it mechanical, be it optical, be it electrical, etc., all the properties of the materials are profoundly influenced by the presence of imperfections or the defects. So, this is also very much clear to all of us, that the influence is not always adverse, often specific characteristics are enhanced. Just for instance, you can see here that the mechanical property, like materials, are stronger when they have defects, right. So, when we consider the example, we can consider pure iron and iron carbon alloy. So, pure iron is soft and ductile, while iron carbon alloy, that is steel, is strong and tough. So, you can see that by alloying, by adding impurity, by mixing two components, or you can say that by increasing the defect, we are just enhancing the mechanical property. So, in this way, the adversity is not there, but the effect is positive. Likewise, we can consider the second example. In the second example, you can see that electrical conductivity decreases when materials have defects. For example, electrical conductivity of pure copper is higher than that of impure copper. So, impure copper containing impurity or unwanted elements, and that is why we study imperfections in solids. Now, if we talk about the crystalline defects, so these defects are basically lattice irregularities in the arrangement of constituent particles. These irregularities are called crystal defects, and crystalline defects occur when crystalline process occurs at fast or moderate rate. So, there are basically 5 major categories of crystalline defects. First is zero dimensional defect. This is also known as point defect. Second is one dimensional defect, or this is also known as line defect. This is due to dislocations. Third one is two dimensional defect, or it is also known as planar defect. And next is three dimensional, which is also known as volume or bulk defects, and last may be considered as vibrations. So, these are the 5 major categories of crystalline defects. Today, we will be discussing majorly on point defects. Now, what are point defects? Point defects are the irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance. So, these can be classified into 3 types. One is stoichiometric defect, the other is impurity defect, and the third one is non-stoichiometric defect. If we talk about the stoichiometric defect, then it is very clearly mentioned that these are the point defects that do not disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamic defects, right. So, these do not disturb the stoichiometry of the solid, that is why these are known as stoichiometric defects. So, these are of 2 types. One is vacancy defect and the other is self-interstitiality defect. So, first we consider vacancy defect. As the name suggests, when some of the lattice sites are vacant, the crystal is said to have vacancy defect. Now, here you can see that a lattice vacancy is equivalent to missing atom or ion, right. Ion, when we talk about ion, then it is the case of ionic crystal, otherwise it may be non-ionic crystal as well. So, if we talk about non-ionic crystal, there is a vacancy defect. So, the number of vacancy is equivalent to the number of missing atom. So, this results, obviously this will result in decrease in density of the substance. These are formed during solidification or produced by thermal vibrations of the crystal lattice. These may be the reasons because of this which vacancy defects are produced when a substance is heated. So, this diagram shows that vacant atomic sites in a structure. This is the vacant atomic site and this is equivalent to the number of atom missing. Similarly, you can see that these are the vacant sites and these are the occupied. These circle represent the occupied sites and this is the vacant site. So, the number of missing atom is equal to the number of vacancies, vacant sites, and in that way this results in decrease of density of the substance. So, this is known as vacancy defect. Second is self interstitial defects or interstitialcy. Now, here you can see that a position on the crystal lattice that is not normally occupied is called an interstitial site. So, this is the interstitial site which is present between the atoms normally present. So, if it is occupied by the same atomic species, because it is also known as self interstitial defect. So, if it is occupied by the same atomic species, it is a self interstitial or self interstitialcy. So, atoms of the same type accommodate into interstitial sites. So, what would be the result? Because of this there would be large distortion. So, they produce large lattice distortion as self interstitial atoms are usually larger than the void spaces or interstitial sites, right. So, whatever we have considered here, vacancy defect as well as self interstitial defects, we are talking about basically non-ionic solids. Now, when we talk about ionic solids, these must always maintain electrical neutrality. So, rather than the simple vacancy and interstitial self interstitial defects, these ionic solids show other types of defects. We name them Frenkel defects and Schottky defects. So, let us move ahead with the ionic solids. So, there are two types of defects in ionic solids. Frenkel defect, when we talk about Frenkel defect, it is actually a vacancy interstitialcy combination, right. So, this defect is shown by ionic solids. You can see here that there is a vacancy and also there is self interstitialcy or interstitialcy. So, it may be called as any atom is being dislocated from here to here, right. So, when we consider the Frenkel defect, this defect is basically shown by ionic solids, right. The smaller ion is dislocated from its normal site to an interstitial site. So, what is happening here? It creates a vacancy defect at its original site and an interstitial defect at its new location. Interstitial defect and vacancy, it is also generated here. So, this is also known as dislocation defect. What about the density? You can see that the atom is dislocated from one place to the other. So, it does not change the density of the solid. So, when we think of the ionic substance having Frenkel defect, then we must understand that it is shown by ionic substance in which there is a large difference in the size of the ions. So, the cation should be very small as compared to the anion. For example, zinc sulphide, silver chloride, silver bromide and silver iodide, because of the small sizes of zinc plus 2 and silver plus ions. So, this size difference should be good enough, so that they any smaller atom, significantly small atom may be dislocated from one side to the other side. So, this is Frenkel defect. Let us come to the Schottky defect. Schottky defect is basically a pair of oppositively charged ion vacancies, right. So, it is basically a vacancy defect in ionic solids. Why? Because we have to maintain the electrical neutrality as well. So, the number of missing cations and anions is equal. If on one hand cation is missing, then on the other hand anion is also missing. So, in that way electrical neutrality is maintained. So, like simple vacancy defect, Schottky defect also decreases the density of the substance. So, in this diagram you can see that the cation is missing and henceforth an anion is also missing. So, it may be called as vacancy defect, it may be called as Schottky defect, and here we can consider the decrease in density of the substance. Now, this is also very important to understand that number of such defects in ionic solids is quite significant. For example, in NaCl there are approximately 10 to the power 6 Schottky pair per centimeter cube at room temperature. Now, in 1 centimeter cube there are about 10 to the power 22 ions. So, we can conclude that there is one Schottky defect per 10 to the power 6 ions. This is how we can say that Schottky defect is shown by ionic substances in which the cation and anion are of almost similar sizes. I think it is very much clear to all of you that this should be the condition, because both the cations and anions are missing altogether, and if they are missing then their sizes must be equivalent, and henceforth electrical neutrality is also ensured. For example, sodium chloride, potassium chloride, cesium chloride and even silver bromide. So, in all these cases the sizes of cations and anions are almost the same. So, this is all about Schottky defect. Now, let us come to the impurity defects. We were discussing stoichiometric defects, then impurity defects. So, a pure metal consisting of only one type of atom just is not possible. So, impurity or foreign atoms will always be present, and some will exist as crystalline point defects, right. So, the addition of impurity atoms to a metal will result in the formation of solid solution or a new second phase. So, here when we talk about the impurity defects, so there are two terms: solvent, which represents an element or compound that is present in the greatest amount, largest amount. So, this is also known, this may be considered as host atoms, and impurity. What is impurity? It may be considered as a solute, an element or compound present in a minor concentration. So, in impurity defects we will consider solute and solvent. So, any foreign atom, the solute, whether it is an impurity or deliberate alloying condition, can occupy one of the two distinct positions in a crystal. So, there may be two distinct positions in a crystal when we talk about the solid solutions. Let us see how. This diagram, tabular comparison shows two kinds of solid solutions. One is substitutional alloy and the other is interstitial alloy, right. So, let us come to the substitutional alloy first. In case of substitutional alloy, this diagram represents substitutional alloy. Here you can see that solute atoms substitute for solvent atoms in a crystalline lattice. Solute atoms substitute for solvent atoms. Impurity is substituted by solvent atoms, not the solute, but by the solvent atoms in crystalline lattice. So, the atomic size difference should be less than 15%. Otherwise, the solute atoms will create substantial lattice distortions and a new phase will be formed. And also the second condition is that crystal structure should be the same, electronegativities should be similar to prevent a kind of ionic bonding, and valencies, if we talk about the valencies, then a metal has a higher tendency to dissolve another metal having heavier or higher valency. For example, here we have considered copper in nickel. So, in copper nickel solid solution, this type is substitutional. Why? Because radii of copper and nickel are 0.128 and 0.125 nanometer respectively, right. So, you can see that sizes are almost the similar. You can see that the difference should be less than 15%. Then they both have face centered cubic structure. This was the second condition, they must have the similar crystal structure. Electronegativities are also almost the same, 1.9 and 1.8 for copper and nickel respectively. So, the most common valency for copper is +1 and for nickel it is +2. So, nickel is having higher valency. So, in that way this last condition is also satisfied, and this is all about the substitutional alloy, copper in nickel. Now, let us come to the interstitial alloy, carbon in iron. So, here you can see that solute atoms carbon, hydrogen, nitrogen, oxygen fit into spaces between solvent atoms in a crystalline lattice. So, it is not about substitution, it is about interstitiality. So, solute atoms fit into the spaces in between the solvent atoms. So, impurity atoms fill the voids or the interstices among the host atoms. Interstitial atoms introduce little lattice strains, since most of the interstitial atoms have atomic radii higher than the interstitial sites radius. So, for metals with a higher atomic packing fraction, the interstitial positions are small in size, and therefore, the diameter of the impurity atoms should be smaller than that of the host atoms. This must be the condition. Now, the concentration of impurity atoms is always low, it is less than 10%. For example, in iron carbon alloys in which carbon is an interstitial atom, maximum carbon solubility is 2% only. So, this is how we can know and understand that what do we mean by impurity defects and what kind of solid solutions are there. There are two categories of solid solutions which we have discussed here: substitutional alloy as well as interstitial alloys. So, the last category is non-stoichiometric defects. A large number of non-stoichiometric inorganic solids are known which contain the constituent elements in non-stoichiometric ratio due to the defects present in their crystal structures. So, these defects are obviously known as non-stoichiometric defects. These defects are of two types: metal excess defects and metal deficiency defects. In brief, we will try to understand that what are these metal excess defects and metal deficiency defects which come under the non-stoichiometric defects. So, this is the diagram wherein you can see that this is the metal excess defects. So, this metal excess defect can occur in two ways. So, this diagram shows metal excess defect due to anion vacancy. So, if the anion is missing, then obviously the number of cations would be higher, and that is why it would be known as metal excess defects. So, here you can see that in this defect a negative ion is missing from its lattice site, leaving behind a hole. Now, this hole is occupied by an electron in order to maintain the electrical balance. Now, the sites containing the electrons are tapped in the anion vacancies. So, the holes are there, the holes are occupied by electrons, and these are known as F centers because they are responsible for giving color to the crystal. So, there are two important things: anion is missing. So, in place of anion there is electron, and these are known as F centers, imparting color to the crystal. This type of defect is observed in those crystals which are likely to form Schottky defects. For example, alkali metal halides like sodium chloride and potassium chloride show this type of defect. So, here you can consider one example when crystals of sodium chloride are heated in the atmosphere of sodium vapor. So, the sodium atoms are deposited on the surface of metal. Now, what happens to the chloride ions? The chloride ions diffuse to the surface of the crystal and combine with these sodium atoms to give NaCl. So, this happens by loss of electrons by sodium atoms. So, sodium ions are formed, and the released electrons diffuse inside the crystal, into the crystal, and occupy the anionic site that we have already discussed, that the anionic sites are occupied by electrons. Now, these electrons are released by sodium atoms. So, sodium ions are formed, these electrons are released, they occupy the anionic sites, and in this way these are known as F centers. Why F centers? Because this has been originated from taken from the German word Farbenzenter for color center. So, they impart yellow color to the crystal of sodium chloride. So, this was metal excess defect by the anion vacancies. Now, there is another method, another way of having metal excess defects by the presence of extra cations in the interstitial sites. So, this diagram represents the presence of extra cations in the sites. In order to maintain the electrical neutrality, if extra cation A plus is present, then at the neighboring site extra electron is also present. So, here you can see that metal excess defect may also be caused by extra cations which occupy the interstitial sites. Electrical neutrality is maintained by an electron present in another interstitial site. We can consider one example here. When zinc oxide is heated, it loses oxygen and turns yellow. So, the excess of zinc plus 2 ions are trapped into the vacant interstitial sites and electrons are trapped into the adjacent neighboring interstitial sites. So, the crystals with this type of defect act as a semiconductor as they contain some free electrons. So, this is how we can explain the metal excess defects by considering two ways: the metal excess defect due to anionic vacancies and the metal excess defects due to the presence of extra cations in the interstitial sites. So, friends, my dear students, in the first session we have had a discussion on crystal structure with a special emphasis on cubic unit cell. We had done a kind of analysis of a cubic system in which we were able to know the concepts of lattice points, atomic radius, coordination number, packing fraction of different types of unit cells. Besides, we have defined the radius ratio, we have understood its significance, and now in today's session we have extended our analysis, our study of solid state analysis, and we have tried to study in detail the solid state imperfections with a special focus on point defects. We will try to know further in our upcoming session. For now, thank you very much. Wish you all the best.